And in addition, for the kinetic energy, well, it's not the same concept. You cannot locate all the mass at the center of mass because there is an additional term with respect to the kinetic energy. So there is a special case of collection of masses, which is the rigid body. So what is the definition of the rigid body? Well, it's a collection of masses. First of all, it's an infinite number of infinitesimal masses rigidly connected together. This is our center of mass. Now our generic element, we're going to call it dm, not mi, because it's infinitesimal. It's like, this is a rigid body. So the infinite number of points, mass points, okay? And they are rigidly connected together. They cannot move with respect to each other. We're going to come to this later. So this is my R vector. And again, the same definition for the center of mass, RC. And this is little r. Okay? So this little r, the distance between, let's say, 2 points on the body, in the body axis, because this is rigidly connected. So the distance between this point to that point, say 1 meter, it will remain 1 meter during the excursion of the motion, will not change, will not deform. Which means that the length of this position vector, relative position vector, the length of this position vector is what? It's constant. Very good. So the length of this position vector is constant, which means if I am looking for its time rate of change, any dot is with respect to what axis? Inertial axis. This guy is not changing its length, but maybe rotating. So I cannot say that the total rate of change is 0, but the total rate of change is what?
Angular.
What's that term?
It's the arm position cross with the angular acceleration.
It's the omega cross r. It's totally due to omega, right? Remember, the rate change of any vector is what? Just differentiate its components. Well, but its components in the body axis are fixed. So this is going to be 0. Plus the effect of rotation, which is omega cross the vector, right? So this is simply here, because of rigid body, this little r dot in the body axis is simply omega cross r. Okay? And we're going to exploit that in our definitions. Any question? So let's define, for example, the angular momentum about the center of mass. This is what? What is the definition? Here is the definition. It's summation of r cross linear momentum. It is. What is it? This black one. Summation of r cross linear momentum, right? This is for collection of mass. Mass is the only difference that I have infinite number of them. So what's the implication? What's the implication? When you go from 1 to 10 up to 1 to infinity. What's the implication? Yeah, is that replace this summation sign with an integral sign, that's correct. And then this r, here is r, cross mr dot, I'm integrating over dm. Okay? So this is the definition of the angular momentum about the center of mass for a rigid body. Now what is this r dot? For a rigid body? So omega cross r. Very good. And I'll go here and introduce some mathematical notation for us to work with. Yeah, I'm done with here. This is great. And now I just need to do a cross product kind of thing.
Am I done?
Yeah, here's m, dm. I'm integrating over the mass. Okay. So the cross product, well, this is generic, not necessarily for dynamics. If you have two vectors, A cross B, this has three components, A1, A2, A3, and this guy has another three components, B1, B2, B3, and I want to do the cross product, do it the way you like, but there is a matrix version of it, actually, which MATLAB uses. You can turn this cross product into a matrix multiplication. We do it like this, A tilde as a matrix, multiplied by the vector B having the three components. Well, what is this A tilde? It's a skew-symmetric matrix. Skew-symmetric meaning zeros all over the diagonal, and Aij is negative AGI. How to fill these? Well, they are the components of A located in a specific way. Negative A3, A2, negative A1. Okay? And it's skew-symmetric, so just get this here in negative, get this here in negative, and get this here in negative. Okay? This is the A tilde, this is the skew-symmetric matrix associated with any three-dimensional vector. Okay? Now I'm going to multiply it with the vector B, which is B1, B2, B3. Here is the result, just simple matrix multiplication. Matrix times a vector gives you a vector. Multiply with me, you'll get A3B2 plus A2B3 and A3B1 minus A1B3 negative A2B1 plus A1B2. The resulting elements, 1, 2, and 3, they are for the resulting cross product. Okay? So we can always turn a cross product in the three-dimensional into a matrix multiplication. This is how MATLAB does it actually. As you know, MATLAB is matrix laboratory, does everything by matrix multiplications. Any question? Any questions so far? Okay, we're going to do the same here because I have omega cross R. Actually, I will say that this is negative R cross omega first because I need this order. Okay? I'll reverse the order simply. And then I'll apply my rule to this cross product. So this is simply, here is the negative R tilde as a matrix times omega as a vector. Okay? Which means that here is HC is the integration of negative I have another cross product, R cross. R cross will be R tilde times whatever coming. Whatever coming is this guy, coming as is. R tilde times omega. And I'll get the omega outside of the integration sign because omega is for the whole body. Okay? Omega is for the whole body, so I can get it outside. So this is a matrix. And actually we call this matrix, anybody can guess? It's the inertia matrix or inertia tensor about the center of mass. So simply, the angular momentum is I omega. It's very analogous to the linear momentum. What is the linear momentum? Is mass times velocity, right? mv. We replace v by omega for angular motion, and we replace the mass by mass moment of inertia for angular motion. So mv is analogous to I omega. Okay? What's this I? We're gonna talk about it in detail, but here is its definition. It comes from here. Okay? Let's talk about I. So our position vector, let's assume that we have three axes. This is x, y, z. So R tilde as a matrix, we know how to construct the tilde, right? Zeros over the diagonal, and then negative third, second, negative first, and do the anti-symmetry. So this is z, negative y, x. So my moment inertia matrix is simply the integration of R tilde multiplied by itself. This matrix multiplied by itself. Okay? Do this, you'll find here y squared plus z squared negative xy negative xz negative xy x squared plus z squared negative yz negative xz negative yz x squared plus y squared dm. We actually call this IXX, IXY, IXZ, IXY symmetric, IYY, IYZ, IXZ, IYZ, IZZ. This is the inertia tensor. It's a symmetric matrix. The ones over the diagonal cannot be negative because you can see here it's all square terms. The ones over the off diagonals, they can be negative. Fine. Any question? You have a question, please? Yes, Joseph?
Is there a physical meaning when they're negative?
For the product's inertia? No. It's simply the mass is tipping over one side of the product over the other side because you see it's